Hey, what is up everyone? I hope all of you are doing great. So from now on, I have permanently changed the name of my channel to StackFi, or should I say StackFi? And do let me know which one sounds better in the comment section. Anyways, the solution of today's question was actually provided by one of my subscriber. I won't tell his name right now. I will tell his name or her name at the end of the video. So stick to the video for the answer reveal. Anyways, in today's question we have two heat insulating pistons connected by a spring can slide without friction inside a horizontal heat insulating tube which is open at both of its ends. 1 mole of a monoatomic gas is filled between the pistons at temperature T1. Okay, at this temperature of the gas the spring is not relaxed. If an amount of heat is supplied to the gas, its temperature becomes T2 and length of the spring becomes eta, that is 1.1 times of its initial length, how much heat is supplied to the gas. Okay, so initially let us consider any one of the piston and considering the other one is at rest, same thing. So atmospheric pressure P0 is acting, P1 is from the inside, and the spring, considering that it is stretched by an amount x, so it tries to pull the piston. Okay, so it is in equilibrium. Similarly, when some heat is supplied, its temperature rises from T1 to T2, pressure increases from P1 to P2, and the final length becomes eta times of the initial one. Okay, so the increase in length, that it's eta times L plus x minus the initial length. So again the piston is in equilibrium, right? So the heat supplies is actually utilized to increase the internal energy of the gas, and it is also utilized to the gas is doing some work against the atmospheric pressure and as well as the spring force also, right? So actually the gas is pushing this piston against the atmospheric force and as well as the spring force. So the internal pressure, of course, it is a monoatomic gas, so it should be, and 1 mole of course, so 3/2 R times final temperature minus initial temperature. Now work done by the atmospheric pressure and work done by the spring. So atmospheric pressure is P0 times the change in volume, so final volume minus initial volume, plus times the, of course, the cross sectional area, final length minus initial length times the cross sectional area, plus half K, a traditional thing for a spring, half K times final extension square minus initial extension square. So final extension is final length minus initial length whole square minus x square. Okay, so just rearranging the first term of this equation. Okay, so initially this pressure, this P0, force due to P0 and the force due to spring is balanced by the internal pressure P1, right? So we got this equation, and similarly in the final situation the atmospheric pressure and the spring force is balanced by the internal pressure P2. Okay, so now we just add this two equation. So adding this two equation we'll get P0 plus Ka times, just in the bracket it should be like this. We have P1 as RT1 divided by initial volume, P2 RT2 divided by the initial volume. Okay, so just add these two terms and we got this one in the denominator. Now I am just multiplying this term with the whole equation. Okay, so at the end we got this one as the left hand side, and on the right hand side we will have this one. Okay, so just rearranging few things, dividing the whole thing by 2, we get P0 times eta minus 1 L plus x times A, and this. Why I am doing this? Because I need to eliminate this term, this L plus x term, right? I don't want this x because x is unknown, and we will get the value of x from this equation. Okay, nice, very nice. So as you can see, I have written this term like this. So here with the star symbol I have with the hash symbol I have tried to show you that these two terms are same. Okay, so eta minus 1 L plus eta x whole square minus x square, just use the formula of a square minus b square, just plug it, a plus b times a minus b, we will get this one, and this one totally matches with this part. So we can write that this term as this one. Okay, now we can easily replace our work done by the atmosphere plus work done by the spring term with a simpler format of this r by 2 eta, eta minus 1, eta t1 plus eta t2. So finally we got this one, and the work done, sorry, the heat supplied is equal to the change in internal energy and the term, final term that we have got. Okay, now there is some mistake in the answer key that has been provided by the book. Okay, there is an additional extra 2 here. Okay, but we don't have this 2. Even if you use their answer and put the values, you won't get the required, you won't get the answer that has been provided in the book. But this result gives you a closer outcome. Okay, that means the result that has been given in the book will near about match with this one. Anyways, you can put the values and find out the result, but I think this one will be the final solution. And thanks to Mr. Nishkal Rao, Nishkal, I think I'm telling it correctly, and thanks for this solution, and you get a cookie. And I hope you all have enjoyed this video, and I'll see you in the next one. Peace, take care.